NASA releases more photos from deep in space. These are among the first from the James Webb Telescope. The first picture was released yesterday. Distant galaxies are so far away.
Captured by the Webb Telescope, one revealing these little specks of light that have been traveling for more than 13 billion years.
At the farthest edges of the cosmos, where light has traveled for over 13 billion years to reach us, the James Webb Space Telescope has unveiled a breathtaking panorama of the universe in its infancy. This glimpse into the depths of space isn't merely a marvel of engineering or astronomy. It is a journey backward through time, revealing the universe as it was shortly after the Big Bang, when the telescope turned its mirrors toward the boundaries of the observable universe. It encountered something both unexpected and deeply profound. The James Webb Space Telescope didn't just see light, it saw structure, motion, formation, and mystery. It saw the raw cosmic canvas being painted by forces we are only beginning to comprehend. Before we start, smash the like and subscribe buttons for more updates. The revelation came in the form of highly detailed infrared images, capturing galaxies so distant their light has been redshifted to the very edge of detectability. These galaxies were not the simple, amorphous blobs scientists had long assumed early galaxies to be. Instead, they were surprisingly well-formed, massive, and complex. The implications were immediate and paradigm-shifting. If such organized structures existed this early in cosmic history, then the current understanding of galaxy formation, which predicted a slower, more chaotic evolution, would need substantial revision. What the James Webb Telescope had uncovered wasn't merely an edge to the observable universe, but a breach in the boundaries of known cosmological theory. One of the most striking discoveries was the presence of what appeared to be mature galaxies forming just 300 to 400 million years after the Big Bang. This timing poses a direct challenge to established models of cosmic evolution. According to standard theory, galaxies should have taken much longer to reach the scale and structure observed in Webb's deep field images. The telescope's near-infrared capabilities allow it to peer through cosmic dust and detect these early light sources in exquisite detail, revealing spiral arms, starburst regions, and even evidence of active supermassive black holes. These aren't the primitive building blocks that scientists had expected. They are fully realized systems, behaving in ways that suggest the universe may have been more efficient at creating order from chaos than anyone had anticipated. This discovery demands a re-examination of how matter coalesced in the early universe. Dark matter, long theorized to provide the gravitational scaffolding for galaxy formation, might play a more dynamic role than previously assumed. Alternatively, there may be unknown mechanisms at work, perhaps interactions between dark energy and matter, or undiscovered physical laws that govern the high-energy conditions of the infant cosmos. Whatever the case, the James Webb Telescope has pulled back the veil on a period of cosmic history that now looks dramatically different from what textbooks have described for decades. Further revelations came in the form of proto-galaxies caught in the act of merging. Webb's observations showed gravitational interactions taking place on a scale and with a clarity never before imagined. The tidal forces, gas inflows, and emergent spiral structures observed in these mergers offered a living laboratory for understanding how galaxies grow through collision and accretion. More than mere snapshots, these were dynamic systems, alive with the motion of stars and gas as they swirled together to form larger and more complex galaxies. Observing these interactions so early in the universe's timeline speaks to a hyperactive era of formation, challenging the assumption that the early cosmos was a quiet, diffuse environment. One of the telescope's most intriguing capabilities lies in its spectroscopic instruments, which allow scientists to analyze the composition and temperature of ancient light sources. From the edges of the observable universe, Webb detected chemical fingerprints of heavy elements such as carbon, oxygen, and even iron, elements that can only be produced in the hearts of stars and then scattered by supernovae. Their presence in such ancient galaxies implies that several generations of stars had already lived and died by the time this light began its journey toward Earth. This pushes the timeline of stellar evolution backward and raises questions about how rapidly star formation proceeded in those first 100 million years. What lies at the edge of the observable universe, as revealed by Webb, is not a boundary in the traditional sense, but a horizon of perception, a limit to how far back in time we can see. Yet even within that limit, the telescope has exposed a cosmos teeming with activity, filled with surprises that defy our most refined models. It forces a deeper philosophical reflection on the nature of observation itself. Every photon Webb collects from these distant realms is a whisper from a time when the universe was young, dense, and hot. A message encoded in light that has crossed unimaginable gulfs of space and time to tell us how things began. This is not just a scientific breakthrough, it is a redefining moment in the human story. The images from the edge are not only data points, they are portraits of ancient light caught in the act of creation. They show us a universe that formed structure almost as soon as it existed, that harbored the seeds of galaxies, stars, and perhaps even life far earlier than anyone had dared to believe. The implications stretch far beyond astrophysics. They suggest that the fabric of space-time, the laws of physics, and the dance of energy and matter may be far more interconnected and elegant than previously imagined. Moreover, the James Webb Telescope's revelations about the edge of the observable universe have reignited interest in cosmic inflation theory. The patterns observed in the distribution and shape of early galaxies might encode subtle clues about the inflationary epoch, the fraction of a second after the Big Bang, when the universe expanded faster than the speed of light. If these observations can be tied back to specific inflation models, they may help to unlock the mysteries of that primordial moment and explain why the universe has the structure it does today. Another layer of intrigue surrounds the possibility of discovering population 3 stars, the first generation of stars ever formed. These stars, composed almost entirely of hydrogen and helium, are thought to have been massive, short-lived, and pivotal in seeding the universe with the heavier elements necessary for planet formation and life. While none have been definitively identified yet, Webb's ability to see deep into the early universe puts it in the best position to find them. If discovered, they would mark the moment when the universe transitioned from darkness to light, from a homogeneous fog of gas to a place where gravity sparked fusion, illuminating the cosmos. The telescope has also begun to probe the diffuse glow between galaxies, uncovering signs of ancient intergalactic filaments, cosmic tendrils of gas and dark matter that connect galactic clusters across millions of light years. These structures, invisible in earlier surveys, now appear as ghostly threads that hint at the vast underlying skeleton of the universe. Their presence at the observable edge confirms predictions of large-scale structure formation, but their apparent maturity once again compresses the expected timeline, making the early universe seem more like a finished painting than a chaotic sketch. Even more astonishing are the signs of potential gravitational lensing near the observable boundary. In several cases, the light from ancient galaxies appears warped or magnified by massive intervening clusters. These gravitational lenses not only provide a natural cosmic telescope amplifying the faintest signals, but also offer direct evidence of dark matter distribution. By studying how light bends around these clusters, astronomers can map invisible mass with unprecedented precision, turning each lensing event into a tool for understanding the hidden architecture of the universe. And yet, for all its discoveries, the James Webb Space Telescope has only just begun to scrape the cosmic surface. The data pouring in from the edge of the observable universe is vast, complex, and laden with meaning. It is a treasure trove of cosmic archaeology, each image a layer of sedimentary light deposited over billions of years. Analyzing this light will take decades, and with each new revelation, humanity inches closer to a coherent origin story, not just of stars and galaxies, but of the conditions that led to life itself. What the James Webb Telescope has found at the observable edge challenges the notion that the universe's beginning was a slow, methodical process. Instead, it paints a picture of a cosmos bursting with energy, racing toward complexity, and establishing the conditions for galaxies and stars with startling efficiency. It forces a re-evaluation of long-held assumptions and opens doors to questions previously thought to be unanswerable. How did so much order arise so quickly? What role did exotic physics play in the first moments after the Big Bang? Could there be multiverses beyond our observational reach, shaped by different initial conditions? Perhaps most profoundly, the telescope's findings reframe humanity's place in the universe. Observing the universe at its edge is like gazing through a keyhole into creation itself. It connects us to an origin point not in myth or philosophy, but in light, energy, and time. The photons reaching the telescope's mirror were emitted when nothing like us existed. Not Earth, not the Sun, not even the Milky Way. Yet here we are, conscious beings able to perceive and interpret that ancient light. The implications of this connection are deeply humbling and equally exhilarating, as more time is allocated to explore even deeper, even fainter targets. The discoveries will likely continue to cascade. There may be fainter galaxies, smaller structures, or even primordial black holes waiting to be uncovered. Each observation carries the potential to upset our understanding or confirm theories that have remained in the realm of speculation for decades. Already, theorists are scrambling to update models of cosmic evolution to account for Webb's findings, and computational simulations are being refined with new data about mass distribution, star formation rates, and chemical enrichment. The journey to the edge of the observable universe is not just a technical feat, it is a narrative of curiosity, courage, and insight. It represents centuries of incremental progress in understanding our cosmos, culminating in a device capable of glimpsing the first flickers of light in the cosmic dawn. And what it reveals is a universe far more intricate, beautiful, and dynamic than previously imagined. A place where galaxies bloom like flowers in springtime, only moments after time itself began. In the shadows of this new knowledge, there remain countless mysteries. Why does the universe look the way it does at such an early stage? Is our model of dark energy sufficient to explain the accelerating expansion across cosmic history? Could there be undiscovered particles or fields influencing early cosmic structure? The James Webb Telescope doesn't provide all the answers, but it focuses our questions with sharper precision, grounding them in newly revealed truths. The edge of the observable universe, once a murky and speculative region, has now become a landscape filled with form and fire, structure and surprise. The James Webb Space Telescope has illuminated this frontier not just with light, but with meaning, ushering in a new era of discovery where the universe tells its story with unprecedented clarity. And in listening to that story, we find not just the history of distant galaxies, but echoes of our own beginnings, etched into the cosmic fabric by the very first light. Beyond the staggering discoveries already made, the James Webb Space Telescope's continued gaze into the edge of the observable universe is beginning to peel back layers of reality that once seemed permanently veiled. Where previous telescopes offered glimpses, Webb delivers immersion. What it sees in the cosmic distance is not just a chaotic primordial fog gradually giving way to order. It sees a universe ablaze with activity and intricacy even in its earliest observable chapters. That early universe is turning out to be far denser with galaxies, star-forming regions, and emergent structures than any preceding model had predicted. Each observation builds upon a narrative of acceleration, as if the universe couldn't wait to become what it is today. Among the most surprising details are the unexpected distributions and shapes of galaxies formed shortly after the Big Bang. Webb's imaging has uncovered an array of irregular, clumpy galaxies packed with intense star-forming activity. These galaxies are not merely placeholders in the evolutionary sequence, they are engines of cosmic change. Some show signs of violent internal dynamics, with turbulent gas flows and high concentrations of nascent stars, hinting at processes that drove galaxy evolution far more aggressively than imagined. They are dense, compact, and extremely efficient in converting primordial gas into starlight, suggesting a set of astrophysical conditions that permitted rapid assembly of mass and luminosity. In these compact early galaxies, scientists have also detected unexpectedly high levels of ultraviolet radiation. This signals an era when powerful starburst events were tearing through hydrogen gas, ionizing the medium around them and helping to complete the epoch of reionization, a key milestone in cosmic history. Reionization refers to the process by which the once neutral hydrogen gas filling the universe became ionized by the first luminous sources. Webb's observations are now giving us the clearest view yet of how and when this transition occurred. The telescope's sensitivity has allowed astronomers to chart the timeline of reionization in unprecedented detail, narrowing down the exact epochs and environmental conditions that allowed light to reclaim the cosmos from darkness. In addition to the galaxies themselves, Webb's instruments have detected vast halos of diffuse gas surrounding them, some stretching far beyond the visible components of these ancient galaxies. These gaseous halos may hold clues about the cycling of baryonic matter in and out of galaxies. Understanding how gas flows into galaxies, fuels star formation, and is then expelled by supernovae and stellar winds is crucial to constructing accurate models of cosmic evolution. The presence of such massive halos so early in the universe's history hints that feedback mechanisms from stars and possibly early black holes were already in full operation just a few 100 million years after the Big Bang. On a broader scale, Webb has offered the first tantalizing glimpses of large-scale structures forming earlier than expected. Cosmic filaments, web-like strands of matter that form the scaffolding of the universe, have been indirectly observed, their shadows falling across the cosmic background. These filaments, composed of dark matter and gas, act as gravitational highways along which galaxies migrate and grow. The fact that they are already prominent so soon after the birth of the universe implies that gravitational clumping was both rapid and efficient. This challenges the notion that dark matter alone shaped the structure of the early universe, suggesting there could be more nuanced dynamics at play, perhaps involving complex baryon-dark matter interactions not yet fully understood. James Webb has also extended its reach into the investigation of the first supermassive black holes. Evidence has begun to emerge of black holes with masses of millions to billions of solar masses forming in tandem with their host galaxies at epochs earlier than expected. These behemoths sit at the centers of ancient galaxies and appear to have grown rapidly. Too rapidly, some argue, to be explained by standard accretion models. One possible explanation is the existence of direct collapse black holes, where massive clouds of gas collapse directly into black holes without first forming stars. Webb may be catching these events in action, providing the first observational evidence for a long theorized but never before seen pathway of black hole formation. The gravitational influence of these black holes is measurable even from this extreme distance, distorting the motion of stars and gas in their vicinity. Spectroscopic data gathered from Webb's instruments helps decode these motions, offering insights into the mass and behavior of these ancient giants. The coevolution of black holes and their host galaxies appears to have started far earlier than previously anticipated, raising questions about the fundamental forces that shape the first complex systems in the universe. Yet, it isn't only the massive and luminous phenomena that hold value. Webb has begun to detect tiny, faint galaxies, dwarfs and proto-galaxies, whose light is just strong enough to be captured with long exposure times. These faint objects are vital for understanding the full range of galaxy formation and the mechanics of hierarchical assembly, where small galaxies merge to form larger ones. Their abundance at the edge of the observable universe reveals a kind of cosmic scaffolding, a population of seeds from which larger systems grew. These faint galaxies may have been key drivers of reionization, their sheer numbers making up for their individual dimness. Beyond the visible galactic structures, Webb is exploring the intergalactic medium itself, the thin gas that fills the space between galaxies. By analyzing how light from distant quasars passes through this medium, Webb is reconstructing its composition and thermal history. The early intergalactic medium was a critical player in cosmic evolution, acting both as the reservoir for future star formation and as the arena where feedback from galaxies and black holes reshaped matter distribution. Webb's detailed spectroscopic profiles are painting a richer picture of this interaction, showing how the cosmic environment itself evolved alongside its inhabitants. And then there's time, an aspect as elusive as it is essential. Webb's observations are helping astronomers build an accurate cosmic timeline by capturing galaxies at different stages of their development. By comparing objects at slightly different redshifts, scientists can construct a frame-by-frame sequence of cosmic evolution, almost like watching a movie in slow motion. This temporal layering allows researchers to trace the birth of elements, the rise of large-scale structure, and the transformation of the universe from a simple plasma to a complex web of stars, galaxies, and voids. But even with the wealth of data from the observable edge, one cannot escape the profound question, what lies beyond? The James Webb Space Telescope cannot see beyond the observable universe, not because there is nothing there, but because light from those regions has not had time to reach us. The boundary isn't physical, but temporal, dictated by the finite speed of light and the age of the universe. Yet what Webb has done is push that boundary closer to the theoretical limit than ever before. The observable universe, once a foggy expanse at the edge of understanding, is now an intricate mosaic of ancient light. The regions beyond may remain hidden, but Webb's findings imply that they too are likely full of structure, motion, and mystery. In contemplating the edge, one must also confront the nature of cosmic inflation and the shape of space-time itself. Some of the features observed by Webb, subtle anisotropies, unexpected alignments, are prompting cosmologists to revisit fundamental assumptions about the geometry of the universe. Is space perfectly flat, or does it possess a slight curvature that only becomes apparent at the largest scales? Could the universe be closed, looping back on itself, or open and infinite, stretching beyond comprehension? Webb's precise measurements of galaxy clustering and light distribution may provide answers to questions that have lingered since the earliest days of cosmological theory. Webb's success in capturing the light from these earliest galaxies is due in large part to its advanced cooling systems and positioning at the second Lagrange point L2, where it is shielded from the heat and light of both the Sun and the Earth. Its instruments operate in frigid temperatures, allowing them to detect faint infrared signals with minimal background noise. This technological triumph is what makes such extraordinary exploration possible. The edge of the observable universe is not bright. It is faint, distant, and diffuse. It takes time, patience, and precision to tease out its secrets, and Webb is uniquely suited for that task. At the heart of this exploration lies a deeply human impulse: the desire to understand where we come from, how we fit into the universe, and what the limits of our knowledge might be. The James Webb Space Telescope has given us a window not only into the early universe, but into our own origins. Each ancient photon it captures enriches the tapestry of cosmic history, adding new layers to the story of matter, energy, and existence. As more data accumulates and analysis becomes more refined, we may discover that some of our most cherished theories need to be discarded or rewritten. Perhaps there are exotic forms of matter or energy influencing galaxy formation that we've never detected. Maybe the laws of physics themselves behave differently under the extreme conditions of the early universe. These aren't idle speculations. They are viable avenues of inquiry ignited by Webb's findings. The edge of the observable universe is proving to be not an ending, but a beginning, a place where new science is born. Even philosophical implications emerge. If the universe formed complex structures so rapidly and prolifically, what does that say about the nature of order in the cosmos? Is the formation of stars, galaxies, and perhaps even life a common outcome when the universe reaches a certain threshold of density and cooling? Are we looking at a cosmos that is predisposed to complexity, one in which consciousness is not a rare fluke, but an inevitable development under the right conditions? These are questions that blend the boundaries of science, philosophy, and metaphysics, and they are fueled by the empirical data returned from the furthest reaches of space. In the coming years, as Webb continues its mission, we can expect the map of the early universe to become even more detailed. Scientists will isolate specific epochs, compare growth rates of different structures, and refine measurements of the Hubble constant and cosmic acceleration. Webb will likely uncover even older galaxies, pushing observations closer to the so-called Dark Ages, a period before stars and galaxies existed. There, in the transition from nothing to something, lie some of the most profound clues about the origin of everything. What's most astonishing is that this journey, this voyage to the edge of time and space, has only just begun. The telescope's lifetime, projected to last well over a decade, ensures that the stream of discoveries will continue to challenge and inspire. With each new image, each new spectrum, humanity reaches further into the abyss and finds not emptiness, but exuberant structure and light. At the edge of the observable universe, we find not silence, but the echoes of a cosmic symphony that has been playing since time began. And now, finally, we are beginning to hear its full composition. As the James Webb Space Telescope continues its meticulous exploration of the outermost boundaries of the observable universe, it is not only uncovering physical structures, but also reshaping our understanding of time, causality, and cosmic scale. The further it looks, the more it seems the early universe was a crucible of activity, a sprawling, dynamic arena filled with phenomena that challenge our most fundamental assumptions. Webb is not revealing a simple linear narrative from chaos to order. Instead, it's uncovering a cosmos that is unexpectedly mature, textured, and evolving at a pace that defies conventional timelines. Among the most revelatory aspects of these observations is the complex interplay between gas dynamics and star formation at cosmic dawn. The telescope's ability to peer into high redshift galaxies has made it possible to study how gas moves into and out of galactic systems in real time. These observations suggest that even the earliest galaxies possessed intricate feedback mechanisms. High-velocity winds, driven by intense starbursts and early black holes, appear to be shaping the interstellar medium, regulating how galaxies grow by limiting or enhancing star formation depending on the surrounding conditions. This indicates a level of internal regulation in galactic ecosystems that was never expected so early in the universe's life. The movement and chemical enrichment of gas at these vast distances offer vital insight into the cosmic cycle of matter. Webb has begun to identify how some elements heavier than hydrogen and helium, collectively known as metals in astrophysical terms, are being redistributed through outflows. These metals, forged in the hearts of dying stars, are expelled into the circumgalactic and intergalactic medium, eventually recycled into future generations of stars and planets. The scope of metal enrichment in such early epochs indicates that stellar evolution proceeded with astonishing rapidity. This affects not only how we understand galactic growth, but also how we assess the likelihood of planet formation, and by extension the early conditions necessary for life. Webb's unprecedented resolution in the infrared has also enabled astronomers to identify forming globular clusters within these early galaxies. Globular clusters are dense spheres of ancient stars that orbit the halos of galaxies, and their origins remain a subject of deep inquiry. Spotting their formation in these early environments provides rare clues about how such clusters came into being and whether they formed independently or within the chaotic environments of merging proto-galaxies. If the latter, this would reinforce the view that the earliest galaxies were born not in isolation, but as the products of intense gravitational interactions, pulling together gas, stars, and dark matter from the surrounding cosmic web. Meanwhile, Webb's capability to analyze the faintest light signatures from ancient quasars, ultra-luminous high-energy sources powered by accreting supermassive black holes, has opened up a new chapter in high redshift astronomy. These quasars, situated at the edge of the observable universe, act like lighthouses, their bright emissions cutting through the dark intergalactic medium and revealing the properties of everything in their path. By examining how their light is absorbed along its journey to Earth, Webb is mapping the distribution of matter, both visible and invisible, across distances of over 13 billion light-years. Each quasar becomes a thread tying together epochs, providing data not just about their own immense power sources, but also about the intervening matter they illuminate. The telescope's observations of these early quasars have also yielded intriguing patterns of variability. Unlike the consistent light of normal galaxies, some quasars exhibit fluctuations over relatively short timescales. This variability may be due to instabilities in the accretion disks feeding their central black holes, or due to interactions with nearby gas clouds and stars. Understanding these changes could unlock the physics of early black hole feeding processes, which remain largely theoretical. Such data also helps constrain the relationship between the growth of black holes and the buildup of stellar mass in their host galaxies, potentially leading to a unified model of early galaxy black hole coevolution. In addition to luminous sources, Webb has begun detecting signals from the earliest examples of gravitational interactions at the galactic scale. Observations of warped galaxies and extended stellar streams suggest that mergers and tidal disruptions were already occurring near the edge of the observable universe. These interactions are the fingerprints of hierarchical growth, the process by which small galaxies combine to form larger ones. By documenting these early collisions in exquisite detail, Webb is creating a time-lapse record of galactic assembly. The tidal tails and bridges of stars stretching between merging galaxies are more than visual spectacles. They are chronological markers, showing how structures formed, collapsed, and reassembled over billions of years. More remarkably, Some of the galaxies at these distances exhibit rotational dynamics, hints of disk-like behavior previously assumed to appear only in more mature cosmic epochs. This challenges the long-standing idea that early galaxies were dominated by chaotic, unstructured mass distributions. The possibility that stable rotation patterns and nascent disks existed just a few 100 million years after the Big Bang implies that gravitational equilibrium was reached far earlier in some regions of the universe than models had forecasted. These observations could lead to new physics being incorporated into models of early galaxy dynamics, including the role of angular momentum in structuring the earliest systems. Perhaps even more surprising is Webb's discovery of isolated systems, small galaxies existing seemingly detached from any nearby clusters or filaments. These isolated dwarfs defy current expectations, which suggests that early galaxy formation was a predominantly social affair involving frequent mergers and interactions. The mere existence of solitary galaxies at such early times raises questions about local variations in matter density after the Big Bang. It suggests that in some regions of space, conditions allowed for early galactic development independent of gravitational clustering. These outliers could provide critical control cases, helping astronomers differentiate between universal and environmental influences on galaxy formation. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what James Webb might find at the universe's edge? We want to hear from you. Thank you for watching, and see you next time.